In this video, we're going to learn a second classification learning algorithm. This algorithm will produce a model that is in the form of a decision tree. Now, if you recall from the previous video, we were looking at this problem in which a credit card company wants to determine whether or not to send a customer promotional materials for a life insurance offer. And so it needs to come up with a model that will predict whether the customer will accept the offer or not. And that model is going to be drawing as its inputs information about the customer, like the customer's age, gender, and income range. In the previous video, we took these 15 training examples, which remember are already classified, and we used the 1R algorithm to learn a model. 1R learned a separate set of candidate rules for each of the input attributes. So one set of rules based on gender, one on whether the customer accepted credit card insurance in the past, one based on income range, one based on age. And then when you look at all of these candidate rules, 1R chooses the one whose overall accuracy is the highest, which in this case is the rules based on age. And that's all that matters in 1R is the overall accuracy on the training data. But when we're building a decision tree, we're going to consider other factors besides overall accuracy, because we'll be able to add in additional attributes that ultimately improve the accuracy. When building a decision tree, we're essentially going to start with 1R, and we're going to view the rules learned by 1R as a simple decision tree with only one decision. So for example, this set of rules that we looked at a minute ago, which is based on the customer's age, you can turn that into a decision tree that looks like this, where you have one branch for when the age is less than or equal to 43, and the prediction there is yes, and another branch for when age is greater than 43, and the prediction there is no. Here's another set of rules based on income range. We can also turn those rules into a decision tree with only one decision. So here is the basic algorithm. Again, we're going to start by applying 1R, but when we choose the rules, we're going to base our choice not on overall accuracy on the training data, but we're going to choose the rules that best divide the examples into subgroups. So what does that mean? Well, take for example these two sets of rules. They are tied for overall accuracy on the training data, and so in the eyes of 1R, they would be equally good. But if we're going to turn this into a decision tree, we have to take into account the fact that the larger the tree becomes, the more likely it is to overfit the training data and to therefore not generalize well. And so we want to somehow keep the tree from getting too large. And so instead of using just accuracy, we're going to use a goodness score, which is the overall accuracy divided by an integer n, where n is the number of subgroups that the rules don't classify accurately enough. And to simplify matters, accurately enough is going to actually be perfectly. So if they don't classify perfectly, we're going to take that subgroup and include it in our number n. So let me show you what that means. Take these rules based on gender. They divide the data into two subgroups, female and male, and you can see that neither of the subgroups is getting perfectly classified. We get 6 out of 7 right for the female subgroup, 5 out of 8 right for the male subgroup. Therefore, our n value is 2 because we have two subgroups that the rules do not classify perfectly. Now again, accurately enough can be defined differently in different contexts, but we're using perfection here just to make it simpler. And so if that's our number n, we're then going to divide the accuracy by n, and that gives us our goodness score, which in this case is 36.5. If we then look at income range, it divides up the data into 4 subgroups based on the 4 possible income ranges. 3 of those subgroups are not classified perfectly. The 4th one is this 50 to 60K group. We get 2 out of 2 of those correct. And so that's not going to factor into our n value. It's just these 3 that are going to give us the 3 for n. and therefore we're going to divide accuracy by 3. And you can see this ends up giving us a lower goodness score than we got over here. And again, the intuition is if we had gone with income range, we would ultimately end up with a larger tree. And by dividing by n, our goodness score will favor smaller trees that have less likelihood of overfitting. And there is a special case, obviously, if n is 0, if everything is perfectly classified or classified accurately enough according to the cutoff that you end up using, then you can just choose that attribute. All right, so if we go and look at the rules we obtained using 1R. So for gender, both subgroups are not perfectly classified, so we're going to divide the accuracy by 2 to get its goodness score. That's the one I just showed you on the previous slide. For credit card insurance, one of the subgroups is not perfectly classified, the other one is. So we're going to divide by 1, and so the goodness score ends up being the same as the accuracy. Income range, we already looked at on the previous slide. We have to divide by 3. And then age, we also only need to divide by 1 here because the subgroup in which age is greater than 43 is already perfectly classified, and so it doesn't count towards our n. N is just 1 because of this subgroup here that is not perfectly classified. So it turns out that the age rules, in addition to having the highest accuracy, also have the highest goodness score, and so our decision tree algorithm is going to choose those rules, and it's going to take those rules and turn them into a decision tree. So we've now carried out steps 1 and 2 of the algorithm on the entire set of training data. We're then going to look at each subgroup created by this decision tree, and in some cases we're not going to have to go any further. So for example here, because this subgroup is accurate enough, in this case it's actually perfect, we're not going to need to divide that up any further. However, that other subgroup, the ones for customers whose age is less than or equal to 43, because we are not getting that subgroup accurately enough, we're not classifying them accurately enough, we are going to now focus on just that subgroup and repeat the algorithm on them, starting over and building a tree for just that subgroup. So in this case, we're going to build a tree for just the customers whose age is less than or equal to 43. Here are the 12 customers from our training data who fall into that subgroup. So we don't have 15 training examples anymore, we just have 12, the 12 in that subgroup. But we're going to repeat the same process over again. We get candidate rules using the same basic process as 1R. We compute their goodness scores. In this case, you can see that the rules based on gender and the rules based on credit card insurance are tied. Let's assume we break the tie by choosing the rules based on gender. We're going to turn those rules into a simple decision tree, and now we're ready to plug this tree into the overall tree. So if we go back to our original tree, remember we were focusing on this subgroup over here. We then applied 1R, but used goodness score to choose the best set of rules. That gives us this tree for just the age less than or equal to 43 subgroup. And so we're going to come over here. We used to say yes as our prediction for that entire subgroup. But now, instead of always saying yes, we're going to make another decision based on gender. So we're replacing this classification with the new decision tree that we just learned for that subgroup. And so now we have a larger tree that does a better job of classifying the training examples. And then we would continue. We would look at each of its subgroups and see if we need to go further. That could potentially make the tree even larger. And we would keep going until we can't go any further, and that would give us our final decision tree model for our training data.